We have here a result that says that whenever we have a one-to-one function continuous from a compact metric space X into a metric space Y, then the inverse, f minus 1 from Y to X, is also continuous. Here, the definition of inverse, just to be clear, is the function such that f minus 1 of f of X returns X. And this for all X in the metric space capital X. For the proof, let us apply that characterization of a continuous function. Remember that said f continuous if and only if the inverse image of V is open for every open set V. So the pre-image of every open set is open. That is the characterization of a continuous function, and we applied to G the inverse of F. Okay, so then the inverse is continuous, as we want to show, if and only if the inverse of G, which is F of V, is open for every V open. Okay, and this V is an open set in X. Okay, so that's what we want to show. We want to show this. Now here the hypothesis we have are that X is compact and F is one-to-one and continuous. Okay, so let's see what we can do. First thing that we notice for, let's say, for some given V in X open, okay, what we notice is that the complement of V, because V is open, is a closed set. Okay, but here's the thing, because VC is closed and X is compact, remember there is that result that says, this is from chapter 2, there is a result that says that a closed set that is a subset of a compact set, then is compact. So VC is compact. Okay, it inherits the compactness of X. Here, it's important that VC is contained in X. Okay. So this is already something, that the complement of V is compact. And then, because F is continuous and the complement of V is compact, okay, we saw in this chapter last week actually that the image by a continuous function of a compact set is also compact. So the image of the complement of V is also compact. Here is where we are going to use that F is one-to-one, okay? Because when F is one-to-one, the image by F of a complement is the complement of the image, okay? So this is because F is one-to-one. And here we are almost set. Because these two mean that the complement of the image of V by F is compact in Y, okay? And a compact set must be closed, okay? So that means it's also closed, and if the complement is closed, that means the original set is open. And this is what we wanted to prove. This finishes the proof. In this theorem, the compactness is crucial, because if we drop it, then the result we just proved is no longer true. Okay, so for example, we could take x, let's say the half open interval 0 to 2 pi, closed on the left, and we could take the mapping f that sends x to y, which is the unit circle. Okay, so we are going to define the mapping cosine of t, sine of t. So basically the image is the unit circle here. There we go. And for every t, we have the point that is cosine sine. Okay, so this mapping is well defined. It's one-to-one and onto. And it's also continuous. Okay, it's continuous because both cosine of t and sine of t are continuous functions. And we saw that when we have that the components of a vector function are continuous, then the vector function f is continuous itself. Okay. And here we can actually compute the inverse. So let's say we have a point xy and we want to find the angle t. Okay, so what we know is that the tangent of t is going to be y over x. So we can compute t as the arc tangent of the vertical coordinate divided by the horizontal coordinate. But remember, here we have the issue, because how is the arc tangent? The arc tangent, because the tangent is something like this, okay, it has its discontinuities. The arc tangent, we need to define it between in intervals of length 2 pi, okay, but it has asymptotes. So this is the tangent, and then the arc tangent is going to look like this. Okay, but clearly when we approach this point, for example, the 1, 0, the problem is that if we look at the point 1, 0, the points t that are close to 0, okay, very small angles, are going to be close, are going to give a point cosine of t, sine of t that is basically 1, 0. But if we go from the other side with angles that are very close to 2 pi, we are also very close to 1, 0, but the t is 2 pi apart from the previous ones, okay? So here we have a jump in t. So we have t's that are very close to 0 and very close to 2 pi on either side of the same point 1, 0. So the inverse cannot be continuous at 1, 0. Okay, so here what we have seen is a function that satisfies all the hypotheses in the theorem except the compactness of the domain X. Okay, in this case 0 to pi, open on the right. And then we see that the conclusion is false in this case.